right. So it's a little different presentation. It will be a lot of data here and not as many simulations. But before I start, I would like to thank Mike and Blacksley for giving me an opportunity to present these results. So I will start with a little advertisement. We published a book this year on zonal jets. There was a lot of talk about zonal jets, but we actually have a big book which deals with it. And it considers zonal jets in various applications, geophysical and planetary, and also plasma physics. So, okay, and it also has a lot of turbulence in it. So it's kind of a compendium, it's a collection of paper on zonal jets in various environments. If I start with telling you what is in the book, I will skip everything, just tell you that we have this big citations from ED, which is very important. That says that any theory of the atmospheric circulation must be based on a theory of large-scale atmospheric turbulence. Moreover, this theory must go deeper than most existing theories of hypothetical turbulence. It is futile to beg the question by introducing hypothetical coefficients of eddy transfer. We have not only to establish the cause of the turbulence, but also to derive from first principles, if possible, of course, its properties with regard to transfer of heat, angular momentum, etc. And just pay attention that it was said in 1950, a long time ago, and he realized the importance of turbulence and underlying physics. Since then, there was a lot of course, paper developed and a lot of work was done in different areas. And even jargon became different in different fields, even though people talk about the same things. So Peter, Reed, and I kind of felt that there is a time to write some kind of a tourist guide for this, because we built a Tower of Babel, and now we needed a tourist guide. So hopefully this will be a good guide. Okay, so let's go to the topic, to the presentation itself. All the geophysical and planetary flows, they have one underlying very important distinction. They are all subject to extra strains. Extra strains are strains which act on turbulence in addition to the basic shear. And it may be stable stratification or rotation or beta effect, which is gradient of the Coriolis force, magnetic fields, streamline curvature, and so on. And they affect turbulence in a non-trivial way. And important thing about this is that when you have this anisotropic extra strain, turbulence becomes anisotropic itself. Also, they introduce waves into the picture, which brings additional complication. And the spectrum changes as well, and it's non-trivial to see a modification of the spectrum because dimensional analysis doesn't work anymore. We have too many parameters and we are stuck with it. For this case, we really need some theory, and we developed a theory which is called the QNSC, quasi-normal scale elimination, which goes all the way back to, it was developed by Semyon Sukharyansky and myself. It goes all the way back to when we started doing it in Princeton with Steve Orsag and Victor Yachot. But the theory was simplified and modified, and it became possible to apply to flows with extra strain, which were not, and waves as well, which were not in the initial theory. And produces some results which I wanted to show how they agree with measurements and with data in various environments. Also, they have some implication for turbulent diffusion. As I said, we all know that, well, we're all familiar with Kolmogorov spectrum, and there is a dissipation rate there, and it may be also a rate of energy transfer. And it applies a turbulence. Turbulence is homogeneous and isotropic. And because of this, well, there is kind of a general assumption that spectra are always, or almost always, determined by the fluxes of energy or entropy. Particularly in geophysical fluid dynamics, this is underlying assumptions for many, many publications and many studies. I think I went back now. Okay, I already talked about extra strain, so I will just move to the next thing. So what about this quasi-normal scale elimination? It's going back to renormalization group by Yachot and Orszag, and essentially what we do, we start with small scales and develop some procedure of small scale elimination. And what it does, it eliminates small shell of scales close to dissipation scale. Of course, dissipation cutoff moves, but the effective Reynolds number remains of the order of 1 around this cutoff. And we do ensemble averaging on small shell of scales. And by computing this, we can rescale viscosity, and if you have diffusion, we can do diffusivity. And if we have some extra strains, such as rotation or stratification, this viscosity and diffusivity, they become anisotropic, and we can see how they will be acting on different direction, and they may be very different, actually. So this theory was initially developed for developing subgrid scale parameterizations for geophysical flows, but as a byproduct, it can compute the spectra, 3-dimensional and 1-dimensional. And we found out that this 1-dimensional spectra, they become very informative in anisotropic flows. And this is what I wanted to show in this talk. So first of all, I start with the viscosities and diffusivities. We have now theory for stable stratification and for rotation, okay? In both cases, you can introduce scales which separate the scales dominated by the waves, internal or inertial waves, and turbulence. In the case of internal waves, in stable stratification, it's Osmondov scale, where epsilon is a dissipation rate and is Brand-Vassallo frequency. And for a case of rotation, it's, well, people call it Zeeman scale, but Woods actually found it 20 years before Zeeman, so I call it Wood scale, which is similar to Osmondov, but we replace Brand-Vassallo frequency by Coriolis parameter, and it has the same dimension. So it's a separation between turbulence and scales dominated by either internal waves or inertial waves. And we can then compare rotation and stratification in this plot, what happens to viscosity and diffusivity. In the case of rotation, we can normalize our wave number with k omega, which is Wood's wave number, and stratification with Osmondov wave number. So when we go to very small scales, the turbulence is just going back to normal Kolmogorov, and it's isotropic. But when you go to larger and larger scales, you can see that diffusivity, in case of rotation, it remains the same, may increase a little bit, but viscosity decreases, goes to 0, and it's evidence of development of inverse cascade due to rotation. Okay, and it's shown analytically. It's a very interesting result. In the case of stratification, the situation is similar if you only do first order expansion in this small parameter. But in the case of stratification, it can be solved completely for arbitrary stratification. So they actually viscosity, it's vertical viscosity and diffusivity. They don't go to 0. They become small, but they remain finite. And then in the limit of strong stratification, diffusivity gives us a very well-known limit of Cox-Osborn mixing coefficient for vertical mixing. For viscosity, it's also, it remains, there is no inverse cascade in stable stratification. This is,
could you say a word about how these curves are computed?
The expressions are very, very lengthy. So they are computed, but the only way you can do it is with Mathematica. You cannot do it by hand.
Okay.
I printed out this equation. It was 3 meters long with type, with font 5, so it's really very difficult to use it. But you can make approximation for it and use it in the models.
It's essentially a perturbative RG control perturbative efficiency.
Yeah, okay. All right. I mean, okay, I have to talk to you more about it. Yeah.
Okay. Now, let's see what happens to the spectrum, because this is what is most interesting.
Are these curves, the RG predictions, are they verified by doing simulations?
No.
Because I mean, in 2D, in these situations,
It's not exactly RG. I need to tell you how to do it because
That's what I was trying to find out, actually.
You can do RG theory with finite number of charges.
but it's only technique of elimination of scales. But what the thing which we want to do is to compute the viscosity and diffusivity. It has different kind of iteration as well. Now this is I wanted to show you what happens with one-dimensional spectra. Okay, it's in the case of stratification, there is a very well-known data for vertical spectrum of horizontal viscosity, and goes back to 1981. It's called composite spectral vertical shear. It can be well, from the theory we get this analytical expression for the spectrum. You see, it has Kolmogorov part and it has stable stratification part, and it can be reorganized in a form of just universal non-dimensional function. So here we compare it with measurements by Gregg, Winkel, and Sanford, which was a little more accurate than initial measurement. And you can see that this is QNSE line, the gray line, for two different depths in the ocean, and it goes right over the data. The slope is different because it's a vertical shear spectrum, so you need to multiply it by k square. So we recover both turbulent part and the internal wave dominated part. And this is theory with no coefficients, with nothing adjusted here. And it's very interesting that it goes right over the data. So this is for vertical spectrum of horizontal velocity in the ocean. And this is one-dimensional spectrum in direction of kz, in direction of k3. Now, the same thing can be derived for potential energy in stratified flow. The spectrum is similar, also has Kolmogorov part and n square k to minus 3, and we can compute the coefficients. There is a spectrum. This is kinetic energy spectrum, but this is prediction of the theory. You can see it goes over prediction in many different environments. It's stratosphere, troposphere, mesosphere, and thermosphere. N is different there, but if you kind of make some effective Brand-Vasili frequency and plot the spectrum, you can see that we are not far away from the data. It's pretty good approximation. In geophysics, what is usually done, it's explained by the theory of internal wave saturation, but this theory doesn't consider turbulence, and it's purely empirical. It just makes assumption the spectrum is determined by internal waves, and if this is the case, then you don't have any other choice but to get the spectrum, but it doesn't predict coefficient and it doesn't tell you what happens with turbulence. On the other hand, what we get from QNSE is analytical expression, and it also works for Venus and Mars. There were some measurements by ANDA using the occultation data, and the temperature and the potential energy spectrum turns out very close to this. So it's another evidence of working in different environment. Now, what happens with the spectrum, if we go back, because it's steep, it has a tendency to accumulate energy on large scale. So this dimension of the spectrum will have more energy than other directions, which are still Kolmogorov. And accumulation of energy in one direction will lead to development of some structure which otherwise you wouldn't see. So in stable stratification, you have layering in the vertical. It's also related to biology, but I just wanted to show you that ocean and seas are vertically stratified and they have horizontal layers, which are a very well-known feature. Now, if we go to rotation, the theory predicts two different spectra. A one-dimensional spectra is longitudinal spectrum and transverse spectrum. One is in the direction of the measure of the line, and another one is normal to it. And after the theory was developed, we started looking on data to compare with analytical prediction. So the first spectrum we thought about was very well-known spectrum from atmospheric science, this, measured by airplane in the troposphere and the stratosphere. It's known like Nasterman gauge spectrum. So when we compared it with our data, you can see the lines in red, they went right over the data. It has two branches, Kolmogorov branch, minus 5/3, and the large-scale branch goes like 8 to -3. And there was, of course, many questions. What is the mechanism of this thing? Is it inverse cascade or direct cascade? And well, not that many questions about the amplitude, but it's still being discussed, debated. From the theory, we can see that it's a direct cascade on these scales and also direct cascade on large scales. So it will be a little bit in, well, quite significantly in conflict with theory of geostrophic turbulence. I will talk about it later. Now, the Nastrom gauge spectra gave us only the longitudinal spectrum. Transfer spectrum was derived from another data set, which is similar to Nastrom gauge, but it's done later on, known as mosaic. In this case, you have longitudinal spectrum and transfer spectrum, and you can see that the theory again predicts it very well. It's from the work by Cadius and his colleagues in MIT and NYU. Now, we have the same thing, accumulation of energy on large scales because of the steep spectrum. And here we have different features. Its large scale feature is a hurricane and other columnar vortices in the atmosphere. Now, we have dependence on the Coriolis parameter in the spectrum, which wasn't considered before. But Nastrom and Gauge, in one paper, they showed kind of variation of the spectrum with latitude. And we plotted different lines from our theory and made some comparison. It's not perfect, but we do see that there is a latitudinal dependence of atmospheric spectra. And what is important, it decreases towards the equator. So on the equator, we only need to have Kolmogorov part. And we do see it in some data coming from satellite scatterometry, also in oceanographic data.
It's all in horizontal dimension.
It's all horizontal now, yes. Now, Charney, in his famous 71 paper, said that it thought that the above theory geostrophic turbulence should also apply to the oceans in the region of strong baroclinic excitation, such as the region of the Gulf Stream, but no observation were available at that time. But since then, of course, we have more observations. So, and in the theory, we see that the spectrum only depends on epsilon and Coriolis parameters. So there is no reason why it wouldn't work for the ocean. So the only thing is to find the data and to see if they do agree. So we checked the prediction of the theory for longitudinal transverse spectrum when available versus observations on the ocean taken with ADCP. It's a ship-mounted acoustic Doppler current profiler. Okay, it's not that many of them are available, but where they are, we could use them. This is Gulf Stream region. It's Western Atlantic. Eastern Atlantic is here. It's a big cross-section between Greenland and Portugal. And this is ACC, Antarctic circumpolar current. We didn't have good agreement south of the polar front, but north of the polar front, we could do it. So this was for the Gulf Stream area. You can see that we have very good agreement between the theory and both longitudinal transfer spectrum. We don't account for the Gulf Stream because it introduces anisotropy, which makes amplitude too large. It needs some correction of the kind of Oliver Buller introduced. So this is just south of the Gulf Stream, and you can see that we have pretty good agreement. This is agreement for this transect for the Eastern Atlantic Ocean, and this is a really very nice agreement going to the small scales. This is for ACC, the same thing. And this is comparison of our model with simulations with MIT GCM with a resolution of about 1/48 of degrees, which is state-of-the-art model. And you can see that this model really suppresses, dumps turbulence on small scales. And I think it's significant because this model is used as a simulator for the upcoming mission called SWOT, satellite mission. And if they think that they can use it as a simulator of small-scale flow, they may have a bad surprise with this kind of subgrid scale parameterization. Yes?
Are you using the same Brunt-Weissel frequency in all these cases? And constant?
Here,
Yeah.
this is neutral stratification. There is no Brunt-Weissel frequency.
Oh.
This is really surprising that the
Why is
theory,
the ocean neutrally buoyant?
it's not neutrally but stratified. But when you look on large scales, the main effect is coming from the effect of rotation, just because n over f is such a large number. It's 100 in the ocean of atmosphere. But what we really need to do is we need to link now what we have for stable stratification and rotation and have a the theory which can consider both effects together. Okay, it has not been done yet, and I think we are lucky that it works just because n over f is such a big number. Now, if we another comparison is here is south of Kuroshio. It's 4 different regions, and this is comparison in every one of these regions. They're separated here. This is Kuroshio, and this is equator. So you can see that the agreement is pretty good for every region. They are very different dynamically. They have very different forcing. Of course, we don't have perfect agreement, but it's pretty close to the data. Now, what is really interesting is that on small scales, it always goes to Kolmogorov spectrum, more or less. So Kolmogorov spectrum is a good approximation of what is going on sub-meter scale. Well, I wanted to show you also what happens on larger scales when we develop regime of zonostrophic turbulence and zonal jets. So this is what we see averaged in the ocean, and this is what we know from the planets. It's another regime, and the spectrum here goes like beta square k to minus 5. It's again, the amplitude is determined by the beta parameter, which is Coriolis parameter, the derivative Coriolis parameter in the meridional direction. Spectrums here is even steeper, and there is more energy accumulating in the zonal direction. And we develop a regime which we call zonostrophic turbulence. This is further development of geostrophic turbulence when you have a beta effect. And the spectrum, as I told you, goes like n to minus, this is zonal spectrum, it goes like n to the minus 5, and the coefficient is beta square. And this is the last thing which I wanted to say. Based on the theory, you can develop diffusivity coefficients, and you can study analogies between diffusion in the sea and on the planets. So this is a dispersion, vertical dispersion of the tracer in the ACC and Atlantic circumpolar current, and diffusivity is constant based on Cox-Osborn model. So this is initial diffusion, and this is the dispersion and time, and this is versus measurements from the ship, and you can see that the constant diffusivity coefficient does a pretty good job here. So that's a comparison of measurements with diffusion. This is horizontal dispersion on Jupiter after collision of the Schumacher-Levy comet many years ago. It was it brought up a lot of debris, and it could be traced from the telescopes and from space stations. And one paper showed what happened with dispersion. So it was initial profile. Impact was somewhere close to the South Pole. And over the time, it was spreading and spreading and spreading, and eventually it became small, and it was untraceable, so it stopped here. But there is an idea that Jupiter jets serve as barriers to the mixing. You can see that they don't stop mixing. Mixing goes very happily goes from the impact point all the way up to the equator. And they couldn't describe it. Sorry, they couldn't describe it without coefficient, diffusivity coefficient, and we could establish this coefficient from the theory. All right, so this is very important, but I probably will talk about it at the discussion. So this is our conclusion.
All right, thank you very much. So this is another talk about geophysical turbulence in the atmosphere and the ocean. So that's myself. We're at the Courant Institute just down the road, and I noticed at any rate, I'm lagging slightly behind. I haven't yet made the transition to widescreen projection, because our projectors at Courant, I think, are not yet capable of doing that. At any rate, so this is work in collaboration with Jinhan Shi, who was a Courant postdoctoral instructor for a couple of years. He's now a tenure-track assistant professor at the University of Beijing. Jon Kallis, who was just mentioned, who was a postdoc at MIT working with Raf Ferrari, who's professor of oceanography there, and is now assistant professor at Caltech. So to start with, it's always good to show some spectrum. And this is a spectral depiction of horizontal scale, so wave numbers here in the atmosphere. I think this is taken at 10 kilometers altitude roughly, and it's the kinetic energy. And what we see here is sort of the numerical resolution at the time of when this slide was produced, which was in 2005. So basically, we were resolving down to scales of a few hundred kilometers and above, and everything below that was parameterized and wasn't represented in the models at all. So I want to use the slide for two purposes. One, to indicate that, well, if you're working on something, you probably don't want it to be directly numerically resolved. So by Moore's law, we of course keep decreasing the grid size, but because it's a four-dimensional simulation, increasing the grid size and reducing the grid spacing by a factor of 10 increases the computational cost by a factor of 10,000. So using Moore's law, that will take pretty much exactly 20 years to increase the grid size, decrease the grid size by a factor of 10 to get an order of magnitude. So you can kind of plot out your career here. So for the young people, you can recommend to work on something that will become resolved by the time they retire. But the most important thing is that we do not believe for a millisecond that what's below those scales that we currently resolve is the kind of the same thing that we're already resolving but poorly resolving above, and that we kind of have some kind of homogeneous progress where we make progress in this direction. It's much different. Every time a new decade or so is unfolded here, there are other physical processes and turbulence kinds that come into play and that kind of challenge the textbook understanding that we have of this whole game. So basically, in this unresolved region, there is kind of a heterogeneous jigsaw puzzle of slow vortices, fast waves, and then super fast actual three-dimensional turbulence. And I would like to take this time to show you a little bit about all three of those. Okay, so always good. Count our blessings. Thanksgiving is just over. The end of year holiday is coming up. We have governing equations. That's a great advantage to other people who have to sit out the machine learning revolution without governing equations. So this is the Navier-Stokes equations as you would encounter them if you take a first fluid dynamics class. So the divergence is 0, the density is constant, and all you can do is you can form a Reynolds number. And then if the only tool you have is a Reynolds number, everything looks like a pipe. No one can resist showing Osborne, forever setting the standards of dress code in British fluid labs. And of course, we've heard a lot about the theory of transition there and the amazing progress that has been made there. But basically, all you do is looking at the Reynolds number and you compute the Reynolds number for the atmosphere, the ocean, they're gargantuan, right? So there was no doubt at the beginning of the last century that the ocean and the atmosphere were in turbulent motion. And here, G.I. Taylor, in one of his early papers on turbulence, he was actually working in meteorology at the time, and he was clearly thinking, this was the beginning of World War I time, he was thinking about these things as turbulent fluids, right? And yet, what actually turns out to be the case, away from boundary layers, the atmosphere and ocean floors are actually devoid of active 3D turbulence. You will not find it. As you know, when you sit in an airplane, it's mostly calm and rumbles only every now and then. So why is that? So the 10 seconds answer to this, oh yeah, it's not a pipe. That's a very short answer. So the larger answer is, well, you need to add these effects, and Boris already mentioned it. The fluid dynamics of Navier-Stokes is fundamentally changed by introducing density stratification as measured by the Brown-Forsyther frequency. So density decreases with altitude. That inhibits vertical motion very strongly and leads to a tendency of homogenizing the flow in the horizontal direction. On the other hand, you also have rotation, which for slightly more subtle reasons tries to homogenize the motion in the vertical and also inhibits a certain way of horizontal motion. So you have kind of two competing anisotropic effects. And from a mathematical point of view, what it completely changes is the linear spectrum of the Navier-Stokes equation. Instead of having a trivial spectrum, you now have a very non-trivial spectrum with a bunch of linear modes that completely dominate the dynamics. And here is a pictorial representation of how big the changes are in the Navier-Stokes equation. These are large changes. It's a large Coriolis parameter and a large buoyancy we've added here to this density disturbance. So the linear terms completely dominate the GFD equations, and that inhibits the classical 3D turbulence very, very strongly. So the linear spectrum consists of fast waves and a slow vortical mode. Here are the fast waves. So this is just the linearized governing equations. And when you solve them, you find waves of frequencies between the Coriolis parameter and the buoyancy frequency, which is much larger. And well, there are internal gravity waves living on the density gradient. Here's a picture. Caroline Müller, who was a student about 10 years ago, she's now a professor in Paris, where's internal tides in the ocean. Unfortunately, I mean, there were so many interesting talks about active fluids. This fish is dead. It's just moving with the flow, I'm afraid to say. But if she had stayed longer, maybe we would have made it move. But the internal waves, the presence of these fast modes, is the reason for the failure of Louis Fry Richardson's personal 1926 forecast, where he tried to predict the weather and it didn't work at all. And because he was a genius, he wrote a book about it instead of burying the results. That's the reason, because he couldn't deal with the fast modes. So his forecast failed because of the stiffness of the problem. So this was overcome by focusing on the slow mode, the same linear equations, now looking at steady modes. And now the pressure field has this marvelous balancing effect. It balances the Coriolis forces in the horizontal, and it balances the pressure forces by gravity in the vertical. So you have this balanced flow where everything is described by scalar potential, this scaled pressure here, which is the quasi-geostrophic stream function. And that gives you the familiar picture of air parcels actually traveling along isobars on the weather map. Why is that? It doesn't go from high pressure to low pressure. It travels along a line of constant pressure due to the balance between pressure and Coriolis forces. So you can base basically, Jules Charney, the grandfather of dynamic meteorology, he figured out that you can base the slow evolution of these systems solely on the dynamics of the stream function, and therefore filtering out the fast waves. And that's quasi-geostrophic dynamic, and that was really, for decades, was the paradigm of successful weather forecasting. What does that do? Well, it makes, for turbulence, which was mentioned, so in the 60s and 70s, if you base everything on the stream function, the conserved energy in the system, say of this form, kinetic plus potential, takes this expression in terms of the stream function, and then there is a potential vorticity, as it's called, which is also a linear operator acting on the stream function, and it's advected by the flow, by the horizontal flow. And that means the entropy associated with this potential vorticity is conserved, and so is the energy, of course. If you combine these two, you get the famous twin spectral constraints, that the energy spectrum has to be such that this integral stays constant, but it also has to be such that this integral times this moment factor also stays constant. And this makes the quasi-geostrophic turbulence very much like two-dimensional turbulence, in the sense that you have the same mathematical structure. In two-dimensional turbulence, you have the energy, just the kinetic energy, and then you have the conservation of standard vorticity, and you get the entropy with that, and you get the same thing. You get this symbol factor k squared between energy and entropy, and their twin conservation leads to the fact that the energy in two-dimensional turbulence and also in quasi-geostrophic turbulence goes upscale, not downscale. And here is a simulation for just two-dimensional turbulence. And what you see here is we're starting with grid noise, and at the beginning it looks like you haven't paid your subscription to HBO, but after a while something different happens. And if you have never seen this before, this is quite remarkable. Out of this complete chaos, this order emerges. It's an unforced, freely evolving, too many buttons. Freely evolving simulation, and these vortices arise naturally after the system organizes itself in these large-scale vortices, which is, of course, where all the energy is at the larger scales. So, the energy is mostly associated with these strong vortices that do their vortex dance, and then all the entropy is associated with the debris, the kind of filamentary debris between the vortices. It's kind of advected like foam or scum on the surface. So it has almost no dynamical activity, but the vortices have all the dynamic activity, but that's where the entropy resides. And you can see all your favorite vortex dynamics going on here. And so this is two-dimensional turbulence, but quasi-geostrophic turbulence behaves fundamentally the same way. In the third direction, it also tries to homogenize and form deep vertical structures.
Is there friction in these calculations?
This is freely evolving from that grid noise. If you had friction, there would be an arrest scale. Here, there is none. I think, yeah, the arrest scale was now. Now it just runs backward in time. There is no large-scale dissipation in the system. So this is just an initial value problem run because it's so easy to do now. It's 1,000 squared. So it's kind of remarkable what we can do now on just to do a little extra demonstration. So there's no attempt made here to reach a steady state at all. It's just to show the vortex dynamics. Okay, so takes care of the slow vortex motions. So these kind of timescales, these are days in the atmosphere, that's our weather systems, and weeks in the ocean. But what about the faster waves? And I mean, I know it's not much time, but I can't resist showing you this letter that Jules Charny wrote. At the time he figured out the quasi-geostrophic theory, he wrote this letter. In the terminology which you graciously ascribed to me, we might say that the atmosphere is a musical instrument on which one can play many tunes. High notes are sound waves, low notes are long inertial waves, and nature is a musician more of the Beethoven than of the Chopin type. He much prefers the low notes and only occasionally plays arpeggios in the treble and then only with a light hand. The oceans and the continents are the elephants in Saint-Saëns' animal suite, marching in a slow, cumbrous rhythm, one step every day or so. Of course, there are overtones, sound waves, billow clouds, gravity waves, inertial oscillations, etc. But those are unimportant and are heard only at NYU and MIT. So it's a marvelous put down. Well, 70 years passed, and this was definitely the paradigm for many decades, but it's not, I mean, now it's not the case anymore. Now we're looking at the kind of coexistence of these things and try to study them together. So here's something that I found. This is a ship track measurements imagine you're traversing a ship through some kind of two-dimensional turbulence like this, but there are also these fast internal waves on top of that superimposed. Is it possible from kind of observations of the spectra observed along the ship, so the spectra of along ship velocity and across ship velocity, if you like, in the direction of the travel of the ship, and you might also measure.
Of current in the ocean.
Yeah, this is simply a measurement, say, along that ship track of the currents. You might subtract, if there's a big large scale current, you might subtract that out. But
How deep?
This example I'm showing, I think, is 100 meters or so deep. So not so. What this is really, I mean, in the first day, there was a lot of talk about remote sensing and line of sight data and astrophysical problems. And it's kind of we share the same problem that we have high resolution measurement on very, very small sets like lines. And if you just look at these spectra in their bare form, well, they look like this. You might draw a power law slope, but you can't unlock whether this is made by two-dimensional turbulence or by waves, say. So we found a way to do a Helmholtz decomposition of these spectra. So basically, we're trying to say that some of these spectra are due to a stream function and some of them are due to a potential. So every observation is kind of split into these two contributions, and then you can find that actually these fields are not independent. They satisfy differential equation. You can solve that differential equation, and you can work out a decomposition formula like this, which gives you all the kinetic energy that comes from the stream function is given by this expression in terms of the observed fields, and vice versa for the potential. So that's what was done with Johan Kallis and Raffaele Ferrari in 2014, and it's very simple, cheap, exact, and useful. We should be so lucky all the time. There's also a step I'm not going to talk about where you can continue to do this and use linear wave theory and actually estimate the wave energy in your field. So when you apply this to the raw data that I just showed, that doesn't unlock its secrets here, when you do the Helmholtz decomposition, you first find that the stream function dominates at very large scales, but then is dominated by the potential. And when you do this wave energy transformation, you find actually that everything is explained by wave energy below a certain scale here, about 100 kilometers or so. So even though it looked just like turbulence, actually it's an intermingling between what seems to be like linear waves at the small scales and then the balanced flow only on top of that. You can do the same thing in the atmospheric data. Boris already showed part of this data. This is kind of mosaic data taken along airlines. Of course, the zonal, the meridional, and they also measured the potential temperature, these three lines. And as Boris mentioned, there's more explanations than there are scientists working on this. There's the idea, it's just like a pipe that's sort of not happening anymore. I added Boris' names here to stratified turbulence downscale energy cascade hypothesis. And then, well, there's the hypothesis that a lot of it is just internal gravity waves. So again, if we sort of apply our method to this, this is just the observed spectra replotted. This is the Helmholtz decomposition, and you see sort of what looks like that the stream function component dominates against the large scale and then becomes comparable or maybe slightly below the divergent component at smaller scales. But if you add to this wave energy decomposition, then you actually find that it looks like this, so that the waves energy actually explains almost all of the observed energy at smaller scales. That doesn't mean that these waves can't transfer energy. I mean, they can, of course, waves can have, by nonlinear interactions, can transfer energy to smaller scales, but it does mean something that it isn't a homogeneous process and that there's a crossover scale where the dynamics fundamentally changes. There are some more wrinkles to the story, and there's controversy about it. I won't go into this, but I was encouraged by the talk by James Phillips, I think, who said he waited 30 years to be proven right or something. I'm not sure I have 30 years of waiting in me, but I can wait another 10 years for people for this to settle down. So what about the ultra-fast 3D turbulence that we know from the pipes? Where does that ever come in? Well, one way it comes in atmospheric and ocean science is not by, we don't have a sophisticated stability theory or puffs theory that we saw in the pipe case. We sort of look at very, very strong events like wave breaking, where it's necessary that there will be turbulence, where we sort of have sufficient conditions for turbulence to arise. So this is like a picture of a gravity wave going into a critical layer, and the waves come in, but they don't come out anymore, and there's sort of necessarily there is a instability and turbulence in this region. So this is an important problem, particularly in the ocean. This is kind of a cartoon of the overturning circulation. The difficult bits to explain are these upwards and downwards moving parts of this conveyor belt, because the ocean is stratified, for water masses to go through the stratification, they need to encounter turbulent mixing, and that's in very short supply in the ocean. So here's a picture that sort of from the 90s that really focused people on the kind of near topography, over rough topography, the 500 meters above that is something. And it's really, the explanation was that these are internal waves, so the fast waves breaking down into the ultra-fast turbulence, and the waves are mostly generated by the diurnal tide, the lunar tide, rubbing back and forth over the rough topography and sending waves upwards that then break and dissipate. So interestingly, so that for the energy needed for this turbulent dissipation comes from the tides and is therefore a sort of heavenly origin. So as some of you might know, the moon, who's hidden here, is going around the Earth, and the tides lose energy by frictional effects and this wave radiation, so the entire system is losing energy. So a little question, there is no wrong answer here. Does that mean the moon is going to fall down in the Earth because it's losing energy, or does the moon go away from the Earth?
Oh, our rotation slows down. We have now 365 days. We used to have 400.
All right, you will ignore this comment. I think that when I'm saying there's no wrong answer, there's only one right answer, but it's you are forgiven to think that if the energy loses system, maybe the tennis ball should fall down, but actually the moon moves away from the Earth at the rate of 3.8 centimeters a year, and indeed, as Gregory pointed out, everything is lost by the rotating Earth. All the energy is actually drained from the spin of the Earth, and also the angular momentum is lost by the Earth, and it's transferred over to the moon, who gains energy. He or she gains energy and angular momentum in this process, and the rotating Earth loses both of it. But what that means is we can measure this very well. We know the energy input into the tides from this observation. So quickly then, I just want to get to so this turbulence is typically measured by direct measurement of the Taylor microscale, very expensive. Wouldn't it be nice if we could do something on the inertial range? And I'm just going to click to the result I want to show you. This is a classical, I have too many pedagogical clicks here. The classical result by Kolmogorov. There's an exact 4/5 law that tells you that the third order structure function, not the second order, but the third order structure function measuring velocity differences between 2 points, should obey this law in the inertial range where epsilon is the energy transfer from scale to scale. That took a while, so I'm just going to skip over the derivation. You can derive this by using the Karman-Hovers-Munin equation. And the interesting thing is that it took until 1999 for this to actually be extended to quasi-geostrophic flows and two-dimensional flows. It was kind of subtly different. But here is kind of the predictions in the inertial range. This is a simulation with 1 billion grid points, and this kind of shows that the tails that are predicted here by these in the large and small scales are indeed observed. So in the last 30 seconds then, can we do better than this? Well, so here's something we did where we do better than this, and we can derive this third order structure function for the entire range, and this is the entire simulation now with this billion grid points, and this is our little theoretical expression for the third order structure function, which you see, that's the blue line is the theory, and the red circles are from this 30,000 times 30,000 simulation. So basically what the idea is that if you could measure the third order structure function over some longer range, you could fit expressions like this and actually find the energy input scales as well as the direction of the energy flow from the third order structure function. And let me just click to so that was a paper, then we did this. Oh yeah. Seems to be the wrong slide. Oh yeah. I thought we managed to do this in a rotating stratified case, but only for the case f is equal to n. I put this it's so embarrassing that it's not a relevant case. I made it a very small font so you can't see it. So it's a special case. But then I mean everything we can make the theory work and everything works very well. There's also a magnetohydrodynamics version of it where we did a two-dimensional version with a magnetic field, and you can do a combined structure function, and you kind of work out the diagnostics. Okay, I'm going to stop here. Sorry.
Thank you. Maybe one really quick question as we switch computers.
To distinguish whether it's colmograph or just wave turbulence, how about plotting according to colmograph scaling? That is, if you have magnitude of energy dissipation or something like that, then you can actually tell whether it is colmograph or wave.
Well, so the thing is, it is almost impossible. I mean, like the -5/3 spectrum that's observed in the atmosphere, say, from these airliners, that's observed on scales, horizontal scales of hundreds of kilometers. It begins there, it extends. It's inconceivable that it would have anything to do with Kolmogorov in the kind of pure form that you can see in a pipe, because there's no flow that has an aspect ratio. I mean, you can't fit anything, right? It would have to be a completely different version.
Well, the old channel flow measurements that Grant and others did, they actually went very far, as you know, 1962. Maybe we could talk later.
I mean, there's no shortage, and people have, and Boris showed, you can fit a lot of power laws to these things. I mean, so what we basically one thing we're trying to get away from the power laws. That's why we have this kind of decomposition.
That's the point I'm making. Actually, it's just not enough to look at the scaling exponent, but also look at the amplitude.
I couldn't agree more. Yeah, or anything else we could on a hold on. Yes.
All right, let's thank the speaker again.
So I'd like to sort of shift gears into stars a little bit, and sort of think a little bit about what turbulence does in stars, and in particular to the angular momentum distribution. So almost all of the turbulence in stars is convection. So this is a movie that Daniel made, Daniel Lecunet. So at the bottom, there's heat being injected into this box, and this sets up an unstable entropy gradient. So you have modes that are buoyantly unstable, they grow, and eventually you saturate in a turbulent state. And so this is the primary way, for instance, that the sun transports energy in the outer 1/3 by radius. And a weird consequence, it seems, is that the sun develops a really strong differential rotation. So here what I'm showing you is the rotation profile of the sun inferred from helioseismology, so from watching sound waves propagate near the surface. So you should think of this as sort of a 2D slice of the sun. The axes are just radial coordinate. And I've labeled the convection zone, which is the outer 1/3. And that's where you see all of this differential rotation developing. And in the radiative zone, which is stably stratified, we don't see any of that. And one thing to really emphasize about this is that this profile seems steady. So there are observations spanning now 40 years of the solar rotation profile in multiple solar cycles. And there's a very small modulation of this, sort of 0.1%, with where you are in the solar cycle. But the average seems to be staying where it is.
Color is frequency.
Yes. So blue corresponds to about 40 days for a rotation period, and the bright red is about 25. So there's been a lot of work attempting to predict this, and it turns out to be very hard to get this either theoretically or even in simulations. And so I want to focus on the easier problem. I want to know what the scale is. And so sort of this is the formula I'm going to be using. So I want to use sort of order of magnitude analysis to get at what the large scale structure of the sun is doing, or any deeply convecting star. Then attach that to a model of the Reynolds stress at small scales, and then solve for the shear. And you can sort of play this two ways. One is that you're making a prediction. If you really believe what your closure model is saying, then you're making a prediction of the shear. On the other hand, if you don't believe it, then maybe you're looking at observations, using that to get this output, and then constraining what your closure ought to be. So that's the goal. I just want to mention the assumptions here. So the sun is very nearly an ideal gas. It's very nearly an ideal MHD. It appears to be axisymmetric, at least sort of in sort of a time average sense. And convection is, for the most part, subsonic and efficient. So we're working at very high Rayleigh number, very high Reynolds number. So there are sort of three equations governing this, which we've seen a few times already. So this is just continuity. The change of the material in a volume is set by advection through the volume. And we have a heat equation, right? So the change in the entropy in a volume is given again by an advection. Here the velocity is a mean velocity. So I want to think about this as a slowly varying quantity. And because I'm sort of doing that separation into slowly varying and fluctuating, there's also a turbulent diffusion term, right? So that's just coming from that separation of scales. And sort of there's one final complication. So if we go into the vorticity equation, we again have an advection term, and then there's a term that comes from closing and getting a turbulent stress. But there's also this thermal wind term, right? So this is coming from the fact that your pressure gradient and your density gradient may be misaligned. And when those two are not aligned, you can imagine running in a circle and extracting work sort of as a Carnot cycle. And so that turns out to be a source of vorticity, and so we need that in there. So those are the equations, and the way I want to parameterize the solution is in terms of these variables. So this is going to be two components of the differential rotation in the vertical direction along the rotation axis and perpendicular to it. There are going to be two components of a mean meridional velocity. And finally, there's this baroclinic angle, which I'm defining here between the pressure and the entropy gradient, just because everything's simpler in terms of the entropy. Okay, so there's sort of one final piece we need, which is how do we take derivatives of all the quantities involved? So the important scale, let's see if there we go. The important scale is this quantity h, which is the pressure scale height. It's the distance over which the pressure changes by an amount of order unity.
Horizontal distance.
That's a vertical distance.
Vertical distance.
Yes, or radial, yeah.
Radial.
Yes, radial, yeah. It points up away from gravity. So that scale really is going to set how all of the radial derivatives act. And the reasoning for this is just it sets the scale for the pressure gradient, and then because your convection zone is very nearly isentropic, that also sets the temperature and the density gradient. Along the horizontal direction, along theta, the derivative, I'm just going to assume that this is all happening at low L, right? So that the characteristic scale is the size of the star. It turns out actually very little changes if you relax that assumption. So you can think about what happens if you have a Rhine scale and an inverse cascade, and it turns out very little changes. Okay, so just as an example of what sort of blurring the equation through the order of magnitude lens does, the advection term, all the derivatives go away except for the ones that we've explicitly said we're trying to estimate. The thermal wind term is just set by the baroclinic angle. And the turbulent stress I haven't done anything to because that's the bit that we need from a Reynolds stress model. So really all the rest of the physics, all the bit that connects to turbulence happens through these quantities P and Q, through the diffusion and the stress. And so what I want to do is sort of think about this perturbatively, at least coming away from the slow rotation limit. So if you think about no rotation, your system is spherically symmetric, and in that limit, it must be the case that these tensors are diagonal in spherical coordinates, right? That's just a requirement of spherical symmetry. And so, if I then break that symmetry, I can talk about going into sort of infinitesimal rotation, and importantly, flipping the rotation axis is the same as flipping the azimuthal direction. And so this tells me which components of the stress are even or odd. And so then analyticity tells you what the lowest order contributions can possibly be. And then dimensional analysis lets you fill in what the stress term scales as. So I should say this is sort of, this is a very naive model, but to the extent that we've been able to compare this against simulations, it seems to agree. These are just other closure models. They all actually give more or less the same scaling as that very simple argument. So I don't want to spend too much time on them. Okay, so then the other limit we need to think about is the fast limit. So awkwardly, if you're thinking about the sun is sort of in between, right? So the sun lives at Rossby number of order 1. Different parts are range from 0.1 to 100. And so you really need to think about both if you want to get that right. And the sun is sort of a slow rotator, so there are lots of stars that are living at very low Rossby number. So in the fast limit, the important thing, as we heard in the previous talk, is that your motion gets really constrained to be along the rotation axis. You get the formation of Taylor columns. And so you can again do something very naive, which is say, suppose that the only remaining unstable modes are those that are within a certain angle of being a Taylor column, right? So you can actually do this in the linear theory exactly, but then you say, suppose that volume factor is the extent to which my convection gets suppressed. And that gives you some different scaling relations. So here, the overall scale of the stress is going down like 1 over omega. It scales like the Rossby number. And importantly, this R phi component, which is what really sets the angular momentum transport, is going down faster. And that's because the modes are getting reshaped by the rotation. So that's sort of all you need to make a theory like this, right? So you have the order of magnitude piece that tells you how these stress components relate to the overall shear, and then you have a model of how those components scale, and you can plug it in, and it's a lot of algebra, but you can get scaling relations out, and these scaling relations are telling you how the two components of the shear, two components of the meridional circulation, and this baroclinic angle all scale. And depending on which limit you're in, you get a different balance of effects. So in the slow rotation limit, this appears to be dominated by either the Reynolds stress or baroclinicity. They both scale in the same way. As you go out to faster and faster rotation, the balance really gets set by the Taylor-Proudman term, right? The term that sort of enforces uniform rotation along the z-axis. Okay, so is any of this right? I think is a very reasonable question to ask here. So here what I'm plotting is the relative shear, and this is going to be horizontal shear in the latitudinal direction, versus 1 over the Rossby number. So rotation rate increases to the right. So all of these systems are inferred from Kepler measurements of star spots, right? So so stars often have spots on them. These are dark. And so as they pass in sort of onto the side of the star facing you, you see the star dim. Taking a Fourier transform lets you figure out that there's sort of a single spot moving around. If you see multiple peaks in your Fourier transform, that tells you that you have multiple spots at different latitudes going around at different rates. And so by looking for systems that appear to have multiple spots, you can measure what this shear is. And by and large, it seems that we've gotten the scaling right. I mean, maybe it's not -6/7, maybe it's some other close power law, but at least the latitudinal measurements seem to work pretty well. So there are lots of other ways that you can measure differential rotation in stars. So I'm just showing sort of comparisons of our predictions versus as many of those as I could make. So on the left here, it's still latitudinal, but this is often being inferred now from spectroscopy. So you can look at sort of splitting of lines, and we also have measurements from Juno of the gravity moments of Jupiter, which also give you internal constraints. On the right are all seismology measurements, right? So by looking at the propagation of modes in stars, or in particular the ones that make it to the surface, you can tell something about what the core rotation rate is and what the surface rotation is. And these measurements are a little sparse, especially on the radial side, but to the extent possible, it seems that this is not too far off, and so that seems to suggest that these very naive notions of how you can close and write down a stress are not too far off. Okay, so this is sort of maybe the obvious comparison that I should have started with, which is what did the simulations say? So on the left are hydrodynamic simulations, and on the right are MHD. And in each case, I'm comparing against the prediction from the relevant regime. So in the MHD limit, it really does look like we've got the scaling right, although I'm a little worried that out at by these 3 points, out at slow rotation, that it seems like keeps going up. And so if anyone wants to run a simulation that's at really slow rotation rate and tell me if the point is there versus there, I'd be very grateful. I'm more worried about what's happening here. So to the extent possible, I've tried to really limit the simulations that I'm including here to ones that are in sort of the matching limit to my assumptions, right? So ones that are ideal, where the convection is efficient, where the microscopic diffusivities are small, the resolution is high. But there still seems to be quite a bit of scatter. So I haven't shown it here, but if you restrict to just one group or one code, the scatter goes down quite a bit. So maybe that's just a difference in reporting. But it doesn't go away completely, and that has me a little worried. Right. So I thought I'd end on that, and that's it.
Excellent. Lots of time for questions. Anyone want to start us off? Srini?
Do I understand then from what you said that the simulations, existing simulations, really don't explain the differential rotation?
Yeah, I would say so. I mean, there are definitely simulations that get the magnitude right for the sun, but I'm not aware of any that get both the magnitude and this sort of peculiar geometry of radial spokes. That may be that I'm not aware of them, but yeah.
Anyone else or anyone on Zoom have any questions for Adam? All right, well then let's thank all our speakers again.